Okay, to finish off 7.3, we've got two examples, one we're going to write in, and the first one that we see printed here. They're basically two proofs. One is a coordinate proof, which is right here with example 3. We need to show that quadrilateral JKLM is a parallelogram. So before we even do the problem, think about what are some conditions we know that makes a parallelogram a parallelogram. We've got our definition, right? Both pairs of opposite sides are parallel. We've got both pairs of opposite sides are congruent, etc., etc. And now you want to think about what we can actually do with the coordinate system. So things we can easily calculate are things like distance, midpoint, and slope. So let's focus on what ways we can prove a parallelogram is a parallelogram by using those three tools. So first off, we can definitely use our definition of a parallelogram, showing both pairs of opposite sides are parallel, by using slope. Alright, so again, option 1, show both pairs of opposite sides are parallel using slope. Remember, parallel lines have the same slope, so that's what we're looking for. Next, we can also do show that both pairs of opposite sides are congruent using our distance formula. So remember, if you're using distance formula, if you can simplify your radical, you do need to simplify that completely. Remember, if you also don't prefer distance formula, you can also create right triangles and do the Pythagorean theorem. Alright, we can also do a combination of both slope and distance formula by remembering that one final reason, which was show that one pair of opposite sides are both congruent and parallel. So remember, for this one, you'd want to use the same pair of opposite sides and do both if you'd like, distance and slope. Remember, again, simplifying your fractions completely, simplifying your radicals. And finally, the last one, which maybe is not as intuitive, but you can show that diagonals bisect each other. And you can do this in a couple ways. You can definitely use midpoint to find the midpoint of each diagonal, and then use that to show that if they have the same midpoints, they are going to bisect each other. But if you don't remember that, you can always find the midpoints and then calculate each half, the distance of each half. But that does a little extra work. So I would suggest if you're going to do the diagonals bisect each other, you just do midpoint. So again, if you show the diagonals have the same midpoint, they are cutting each other in half because they both intersect at the same midpoint. Okay, so again, if you're using that last one, that fourth option, we want to show they have the exact same midpoint, which means they end up cutting each other in half. Okay? So remember, these are 4 different options. You definitely don't need to do all 4. You just pick the one you like best. And you can always use that for every single one of these types of problems. So personally for me, I like counting slopes, so I'm going to use option number 1. So let's go ahead and graph our parallelogram, and then we can write our coordinate proof. Alright, so there's my parallelogram. Then remember, we don't want to assume anything, so we don't want to just look at it and say it's a parallelogram. Start with your givens. Our givens are the coordinates. And I always like to write my coordinate proof as a modified paragraph, so I'm going to keep doing that pattern here. Alright, so starting with my given, which is just those points, and like I said, I am going to focus on option number 1, so I'm going to show both pairs of opposite sides are parallel using slope, so my next step is going to be my slope formula. Okay, so those are my 4 slopes, right? 3/4, -5/3, 3/4, and -5/3. So we can already see that this is looking great, right? Because we want same slopes to show parallel. Remember, alternatively, if you don't want to use that slope formula, feel free to tell me you counted, but always count, your rise over run and get the appropriate numbers and signs. So then this is pretty much going to write itself now. We're just going to substitute to show that the slopes are the same, and then talk about the sides being parallel. Alright, so that means that, again, substitution to show slopes are the same, and thus if slopes are equal, our sides are parallel, and then finally, we can just wrap up by saying exactly what we want to say, that JKLM is a parallelogram because opposite sides are parallel. Alright, and that wraps up example 3. So remember, you can also write definition of parallelogram for this one reason, but again, if you don't want to remember, wait, what's a definition and what's a theorem, just explain it, and that's fine. Alright, so then hopefully you left some white space underneath this because we're going to do one last example, which is just a normal proof. So let's go ahead and write that one down. Alright, so there's our last example, a regular old proof, so do whatever you'd like to, column, flowchart, paragraph, but here we're given a quadrilateral ABCD with diagonals drawn in. Angle 1 is congruent to angle 2, and oops, it'd be helpful if I showed you where those are. Angle 1 is right here, and angle 2 is right over there. And then we know BD bisects AC. So remember, what does bisect mean? Bisect means to cut in half. So if it helps, you can start marking up your diagram with what we know from the given. So right, I know that angle 1 is congruent to angle 2. And then I know BD bisects AC. Again, bisect means to cut in half. So that means BD isn't being cut in half, right? BD is cutting AC in half. So that means, let's call this point E, but AE is congruent to EC. All right, and then we want to think, well, how does this show me that this is a parallelogram? But remember, you have options, right? We have 6 options. We can show both pairs of opposite sides are parallel, one pair of opposite sides are both parallel and congruent, etc., etc., etc. So that's where sometimes the tricky part is. We want to think, well, wait, what does this actually tell me? And what options are actually viable options? So what I want you guys to see right here is look at these angles. These angles are actually key in this proof. What kind of angles are they? Well, remember what we just talked about in class? If you can create this Z or that zigzag with your 2 angles, we have alternate interior angles. And remember from Unit 3, if you have alternate interior angles that are congruent, that shows us AB is parallel to CD. So I'm going to write a little flowchart here to start putting down my connections. You guys feel free to do whatever method you like. All right, so again, we can tell because those alternate interior angles are congruent, AB is parallel to CD by the converse of the alternate interior angles theorem. So if that was something that you're like, oh gosh, I don't really remember those, go back and look at Unit 3 or Chapter 3 in your textbook and want to review those reasons. But again, I can see they're alternate interior because of that Z, and they're congruent, which make those lines parallel. And that was key for me, because then I know I only have 2 possible options to work with. So my 2 options are right over here, right? I can show both pairs of opposite sides are congruent, or I can show, not congruent, are parallel. Let me fix that. Or I can show that one pair of opposite sides are both congruent and parallel. And that's because I already have one pair of parallel sides. So I don't want to go ahead and say, okay, look, what can I do to find my, congruent opposite angles or whatever. So we want to go ahead and use what we know now to help us figure out either that BC is parallel to AD or that AB is also congruent to CD. So that's where this bisector comes in, because it's like, wait, why do we know this bisector? How is this important? Well, if I look at this diagram as just this little bow tie of 2 triangles, I can think, well, it tells me that AE is congruent to CE, so I can think about things like SAS, ASA, AAS, HL, and SSS. And if I can show those triangles are congruent, you guys remember CP, CTC? Then I can show that AB is congruent to CD. Alright, so let me just undo these yellow highlighters for a moment, and let's just look at those 2 triangles. Let me highlight those triangles. So what I'm talking about is this, right? If I can show that these 2 triangles are congruent, then I can use CPCTC to show that the sides AB and CD are congruent. Right? So then how do I show these triangles are congruent? But remember, anytime you have this bow tie, what kind of congruent angles do we see at its intersection? Well, we're going to see those congruent vertical angles. And there we have angle, side angle, angle, side angle. So let me go ahead and finish writing my proof. So the second given, BD bisects AC, tells us that AE is congruent to CE by the definition of a bisector. Oops, that was given. And then completely separately, right? Anytime we have that bow tie, we can always talk about congruent vertical angles. So we can say angle AEB is congruent to angle CED by the vertical angles theorem. And then using the fact that angle 1 is congruent to angle 2, AE is congruent to CE, and our vertical angles, we've got, I'm going to flip this one over here, ASA. So triangle ABE is congruent to triangle CDE by angle side angle. And that was a lot of work, but we don't want to be done here yet because we're trying to prove that we have a parallelogram. So remember, I want to use ASA to then show us that AB is congruent to CD. Remember CP, CTC, corresponding parts of congruent triangles are congruent. So now I have the same pair of triangles, or excuse me, the same pair of opposite sides being both congruent and parallel. So then ABCD is a parallelogram. And that's because one pair of opposite sides are both congruent and parallel. And we're done. So I know these arrows kind of went a little all over the place, so if you can't read that, if you want to make this into a 2-column proof, I can tell you really quick what the order would be. So there's a couple ways to do this, but here's one option. This would be statement 1, statement 2, statement 3, statement 4, statement 5, 6, 7, and 8. Alright, if you'd like me to rewrite this in a 2-column proof, just feel free to talk to me about this tomorrow in class. Otherwise, we are all done with 7.3. Alright, please make sure you let me know if you have any questions, and thank you for listening.